Hello everyone, let's talk about page 15 in our Earth and Space Science Reference Table, Geologically Important Radioactive Elements used for radiometric dating. Alright, so let's look at the top of our table. We have a parent isotope, we have daughter decay product, we have half-life that we measure in years, we have a useful dating range also in years, and then we have datable materials. Let's look at each column. First one, parent isotope. That's the original radioactive isotope that we're going to be starting with. Remember, isotope is heavier than actual element due to extra neutrons in its atom. So we have our samarium, rubidium, uranium, potassium, and carbon. Next column is a daughter decay product. These are the elements that we get when the parent isotope disintegrates. Okay, it's going to turn into these daughter products. Next, we have half-life. That's in years. How long is it going to take for parent isotope for half of this amount to break into a daughter isotope? So for the first one, we see that it's going to take 106 billion years for half of it, for 50% of it, to turn into a daughter isotope, and so on. Next column is useful dating range. We use these numbers to figure out which element we are looking for and what are we planning on dating. For example, dinosaur bones are too old for us to use carbon. Carbon is only between 170,000 years for their dating range, and dinosaur bones are older than that. We're going to be using a different isotope for that. So basically, useful dating range helps us figure out which isotope we use depending on how old something is. Finally, the last column, we have datable materials. Where are we going to find this isotope? So like garnets, micas, organic material for carbon here we see, glacial ice, things like that. We have potassium-bearing minerals for different uranium-bearing minerals for uranium, and so on. So let's look at the top of our chart. Let's look at one whole line. For example, parent isotope samarium 147 is going to break down into neodymium 143. How long is it going to take for half to break down? It's going to take 106 billion years. So if I want to have two half-lives, for example, it's going to be 106 billion years times 2. Okay, and I'm going to have 212 billion years if the two half-lives passed. Okay, so if we start with 100% samarium, we half it. Okay, it's going to be only 50% samarium left and 50% neodymium. If it's the second half-life, I'm going to half it again. So instead of 50 now, I'm going to have 25. But that 25 is going to go onto my daughter product. So the ratio is going to be 25/75, and so on. Every time half-life passes, we are breaking our element in half. Okay, and then useful dating range is between 10 million and 1.6 billion, which is the age of our planet. Okay, and what do we use for these data? What are the datable materials we use? Is garnets and micas. All right, so as we look at the top of our chart, all of our elements here are the dating range is ending at 4.6 billion here, which is the age of our planet. Mostly we use it to date older materials, and then the only one that's different here is the carbon. And carbon here is used to date organic or living materials, glacial ice, carbon dioxide, groundwater, and ocean water. Okay, the half-life of carbon is only 5,730 years. And here's my dating range for carbon. All right, I hope that was helpful, and good luck studying.